Hello everyone. Today I will talk about yet another um, unusual, however promising alternative to Einstein theory of gravity discovered by Hermann Weyl. Some of you might remember that it's not the first time I'm reviewing a theory of gravity with the name Weyl in it. It's the most famous of the theories usually called conformal gravity, and that this is another one. It is actually related, however, it's a bit different, and experimental predictions will also be slightly different. So let's start. Okay, I'll just follow this historic review published recently. In 1918, Weyl introduced Weyl conformal geometry and associated quadratic action, which was the first gauge theory of spacetime symmetry, the Weyl gauge theory of dilation and Poincare symmetry. The initial physical interpretation of his theory was, however, short-lived and led to the downfall of Weyl geometry as a physical theory. Yeah, okay. So what is he talking about here, and what happened? First of all, let's talk about general idea. Where does it come from? As you might have heard, Einstein himself was inspired by the Mach's principle, which he himself was inspired by Leibniz, and by the rejection of Newton's absolute space. So yeah, this absence of absolute space means motion is only relative, and it also implies that certain operations which we could perform with our coordinate description should leave our observable quantities invariant. I think the following argument due to us, at my memory, it's even on Poincare. Let's say we have, some rulers, some physical bodies, clocks, and so on. And it seems like if we just take, and multiply the size of the ruler by 2 and the size of all the objects by a factor of 2 and do the same with everything, nothing will change, right? Nothing will change as soon as there is no absolute space, right? So it seems like a theory which has no absolute space, if it's ever described through some sort of coordinates on some four-dimensional manifold auxiliary mathematical notion, it should have this symmetry where we could rescale every distance by a factor, and the observable shouldn't change. So that's put in as a guiding principle into this Weyl gauge theory, and later it's promoted to a local symmetry, similarly how it's done with U1 theory of electromagnetism, with the introduction of auxiliary vector field. So yeah, so that's what determines the field content of this theory. We have a metric on our four-dimensional manifold, like an Einstein theory, but we have an additional gauge field. And everything is symmetric with respect to the following Weyl gauge transformations. This is the rescaling of all lengths, and this is a standard gauge transformation acting on a vector field. So the main difference with Einstein theory is that now the connection which we have is not a metric connection. So the metric tensor is not annihilated by the covariant derivative. Covariant derivative of the metric is non-zero. Instead, it's precisely controlled by this gauge field. Okay, so now what what Einstein said about it. Yeah, however, look, the original interpretation was that this omega mu should have been the photon. This turned out to be not true, but well, it didn't play a very important role for the future. Yeah, so Einstein originally was quite excited about it. He liked, because again, Einstein liked this idea of absence of absolute space, but he saw a problem in it. He said that, well, look, if you have a non-zero covariant derivative for metric, this means if you parallel transport any, clock around a closed path, the clock rate will change. So the clock rate becomes path history dependent. Yeah, that means that two identical atoms transport along different paths from an initial to final place end up with different spectral lines, contradicting experimental evidence. So yeah, that seems like the theory is immediately ruled out. And for this reason, people forgot about it for a long time. This, however, turned out to be not quite accurate. Actually, this argument turned out to be invalid. In a sense, it arises from certain misinterpretation of the quantities introduced in the theory and its their relation to observable quantities. So, first of all, one can notice that the following combination of connection and gauge field actually annihilate the metric tensor. And this 2 is precisely, the space-time charge, Weyl charge of the metric. So in general, we could define for every tensor with such Weyl charge Qt a new connection, which just depends on this charge. Such that the covariant derivative of this tensor will transform covariantly with respect to gauged Weyl transformation. And for this new connection, the metric will be constant. Therefore, this new connection is a metric connection. And this is the one which is supposed to have direct physical interpretation. However, now it depends explicitly on this auxiliary field omega. Okay, but it allows to build us the analogs of Riemann tensors, Ricci tensors, and Ricci scalars, just like in a usual GR, except for everything is now omega dependent. However, as an advantage, they are all Weyl covariant. As you probably know, the standard where it was the standard Riemann tensor, and therefore Ricci curvature and Ricci scalars are not conformally invariant. Yeah, as you can see, if we change the metric like this, the Riemann tensor changes non-covariantly. So here everything is Weyl covariant. And these quantities, these new Riemann and Ricci tensors with heads, they could be expressed in terms of the usual one and these additional terms involving omegas. So what is the advantage of this? The advantage is now we could build a Weyl gauge covariant actions out of these quantities. And the simplest one is just quadratic in curvatures, in scalar curvature and field strengths for omega. Now, what is the physical interpretation of this action? As you remember, when I was talking about Weyl conformal gravity, it also had a quadratic action in Weyl tensor. However, well, experimental predictions of this theory were very different from Einstein theory. There were different gravitational waves, way weaker, seems inconsistent with observations, different behavior of galaxy rotation curves, different behavioral potential. Seems like there were contradictions, and so on. And if you remember, there was Hooft paper claiming that conformal gravity is equivalent to Einstein gravity with additional scalar, and if you try to integrate the scalar out, it leads to divergences, so you can't get rid of it. Here everything is better. Here we can introduce additional scalar such that if we integrate it out, we will get this action back, right? It's the standard trick. We could actually get rid of it using Higgs mechanism. So at first, if we assume that it requires a wave, we could pick a gauge where this scalar is just destroyed. And what's great about it is that at the same time, its vacuum excitation value sets the scale for all other physics. It determines both the cosmological constant and the Planck's constant, the Planck's mass. So basically the gravitational constant. And also it automatically gives mass to this auxiliary gauge field. So as a result of that, in low energy limit, this additional auxiliary vector field becomes massive. So that's why we don't see it. And we're just left with Einstein theory. Therefore, the at least immediate physical predictions of this new theory are the same as Einstein theory, and it starts to deviate from it only at the Planck scales. Well, actually, well, yeah, I mean, the scale controlled by this dimensionless parameter xi. Okay. Yeah, and this scalar field will be eaten up by the gauge boson, so it doesn't matter. Its fluctuations don't matter. Okay, so this is good news. You could also add the standard Weyl tensor squared term as again conformal gravity. Yeah, there's a question about whether it produces ghosts. As you remember, I discussed them separately too. It's not that simple. And you could also add a topological term. So now let's talk about quantization. Because usually this Weyl symmetry suffers from Weyl anomaly. It's immediately destroyed on quantum level, so the gauge theory of Weyl symmetry wouldn't be consistent. Here, however, everything works fine. Well, the authors immediately decided to use dimensional regularization because that's, the best chance to save uh, the gauge symmetry. And it's turned out that in dimensional regularization, this action possesses a canonical regularization. So you don't have to introduce new scales which will break the Weyl invariance. You could just add a term like this. So the action is actually well defined in d dimensions. So yeah, that allows everything to went through smoothly, supposedly. I don't know whether there are any other underwater stones here. And finally, what's even more interesting, that this action actually possesses a Born infinite-like generalization, where these quadratic terms here are just the first order terms in the expansion of this non-Bugoto-like, or more correctly, Born infinite-like determinant of some matrix built out of Ricci scalar, Ricci curvature, and the field strengths of auxiliary field. Oh yeah, this action is kind of remarkable. Yeah, this WDBI action is an elegant generalization of Weyl quadratic gauge theory of gravity and unique among gauge theories since it does not need a regularization. Yeah, only pure analytic continuation by replacing d with d minus 2 epsilon. To appreciate this, note that not even in string theory can Weyl symmetry be respected at quantum level. So an additional condition of vanishing beta function is imposed. And finally, yeah, just like with the Weyl theory, we could discuss the coupling of this gravity to conformal version of standard model, which I talked about in one of the videos before. And everything seems to be fine. And what's more interesting, that this coupled theory also possesses a generalization of this form of determinant of something. Now, it just, this something is way more complicated. Yeah, the matrix A mu introduced here has to be replaced with this huge expression with all the fields in the standard model. Yeah, so that's kind of neat. But it raises a question, well, how do we even should approach the question of quantization of gravity? Well, there is some theory. It seems like it's okay. Well, it agrees with Einstein theory on observable experiments. Doesn't have really new effect predicted, except for those on high energies. So, like, what should we think about it? Is it just wrong or irrelevant or what? Yeah, that's kind of undermines the whole approach to our modern theoretical physics. I don't know. Well, I hope you enjoyed this video. Maybe not, but just if you're interested in unusual theories of gravity, that's just another one in your collection. I hope I'll find something more significant, and if I do, I will share it with you. See you next time.